Good afternoon, and I'm Trevor Tao from ARM. In this afternoon, I'm in the networking team of the ARM. And in this session, I would like to talk something about how to empowering high-performance user space network stack on ARM. I will talk about the problem statement, some introduction about our topic, our user space TCP/IP stacks on ARM, and mainly I will talk about Fstack, which is developed by Tencent and as open source projects. And the second topic, the second user space TCP/IP stack is mTCP, which is developed by a Korea university, and the VPP Hoststack, which is integrated in the VPP stack itself. And I will give an initial comparison between the current user space network stacks. And finally, we'll talk about some of our next steps. And as we know, DPDK has low layer, high performance packet processing functionalities, which surpasses the kernel. And the kernel bypass can avoid the performance bottlenecks caused by kernel packet copy, thread scheduling, system calls, and interrupt. And the user space socket configuration is much more flexible. Due to kernel space limitation, the maximum TCP buffer is 4 kilo. And the user space sockets are not subject to this limitation. And for example, Fstack's default maximum TCP buffer is 16 kilo. And with the traditional slow pass, we have a NIC and a Linux kernel network stack and application. For the user space TCP/IP stack, we have DPDK as the network driver. And we use the user space network stack as the TCP/IP stack. And on above is for the application, which forms the faster pass, and compared with our traditional slow pass. And when we talk about the user space network stack, we would like what features and performance benchmarks we would like to consider. The first one is dependency. And dependency means can it be delivered at an independent library? If yes, which other libraries are required? If not, which other software modules are required? The second thing is about DPDK support. And I think every current user space TCP stack integrated with DPDK. And the third one is the UDP support. And some of the user space TCP stack cannot support UDP. But most of them, I think, can support. And the socket interface. And does it support the socket interface for application? Some of the socket interface is the same as the legacy BSD socket. But most of them is a little different. It is modified from the traditional BSD socket. But they are very similar. So if they don't use the same socket interface, the legacy applications cannot directly run on this socket interface if cannot be ported. So for Fstack, for mTCP, we still need to do some porting for the traditional applications. I will talk about it later. And another feature is about the advanced TCP options. Can either support SACKs, time stabbing, window scaling, selective active ACKs. And a very important feature is about multi-core scaling. And as we know, the kernel space is very restricted. It cannot support multi-core with a good performance. But for the user space network stack, it can support multi-core, very good. And the stretch code values we care about is about the throughput, the bandwidth for applications for large small data transfers, such as for different kinds of file size, such as 1K, 10K, and 1 mega file, and even more large file. And for the user space application performance, some other benchmarks are the request per second, RPS, and collection per second, CPS. Firstly, I would like to talk about something about the Fstack. Fstack is developed by Tencent, and it's very high friendly, and a lot of features that we desired. Something like ultra high performance, which a network card can achieve on the full load, and full user space. And it has a totally FreeBSD-based network stack, which provides a complete and stable stack function with the network tools such if config and the net state and the root, something all that like that. Now Fstack can support the Nginx, Redis, and other mature applications. And it is easy to extend to multiprocess architecture and provides micro-thread interfaces. And various applications with stateful applications can easily use Fstack. It provides ePower KQ interface to allow many kinds of applications to easily use Fstack. As this graph shows, at the low end is the DPDK. And the second layer is the FreeBSD, and the third layer is POSIX-like API, such as socket interface. And it's on the above is SDK and IPP. But Fstack also has some limitations. First one is the multiprocess architecture not suitable for micro-thread. The second one should modify the application source code, as it don't support say traditional BSD sockets, but with a little modification. It cannot be used for multiple apps, which means that we cannot do independent processes besides the DPDK processes. This graph gives out the Fstack changes to FreeBSD TCP/IP stack. Actually, Fstack do some modifications to the legacy FreeBSD stack, such as the memory malloc, such as the timers, such as kernel process scheduling, and polling, and remove some of the mutex or something read-write logs, something like that. We had done an initial performance evaluation on for Fstack's applications. First applications is about Nginx is a very very popular web server applications. This for the left. So the left graph is about the 600 hash bytes body bandwidth test, which is bandwidth. And for the server, on server side, we compared the Fstack to the traditional kernel stack. We see that for the blue block is for the kernel, ARM kernel, Ubuntu kernel side performance, and from the black box, it is about the Fstack performance for Nginx.
Yes. The generator was on the same host?
No, across hosts.
Across hosts?
Yes, with WRK and on another host. The client is x86.
So it went out the server to and back? Just the stack was user went, but it went out and back?
Yes. Two across two hosts, and one is for server and client. But the client is x86.
Okay.
Oh. Okay. And we see that with the same number of CPU cores, Fstack Nginx performance is much higher than the kernel, almost double of the kernel. And the right hand is the request per second RPS performance. And we also see that the Fstack performance is very higher than the number of servers, number of CPU cores, and it is at least about 2 times in the traditional kernel side. And it scales very well with the number of CPU cores. Another thing we are doing is that is a work in progress, but it's still work in progress. Is we are transplant the iProof3 to Fstack. We are doing this since now. But the legacy iProof works on a rather different model from that of Fstack. So there are a lot of challenges we have to face. The first one is that the legacy BSD socket and the file operation based. The iProof is based on the legacy BSD socket and the file operation. So we have to adapt them to the Fstack's API, such as the FF socket, such as the FF listen to the traditional legacy iProof3. And some of the file operation is also different. For example, we want to set the socket to be non-blocking. The 2 kinds of things are different. And another challenge is that for the Fstack, it uses a large value of the socket. It is more than the traditional legacy FD set size of which is usually set to the 124. But for Fstack, the socket number is much more than that. When you use the traditional FD set operations for Fstack, it can be crash. They can crash. So a solution about that is we use a user-defined, C library to integrate to iProof, and which can set the FD set size to a larger value. And another very important challenge is that for some of the operations, iProof operations such as read, we think read is blocked if there is no packet arrived. But for Fstack, all the operations can't be blocked because the lower processes, DPDK process, need to receive packet. It can't be blocked. So this is very challenging. So all the operations in Fstack is not blocking, is not blockable, such as FF select is a little different than the select. The select can be blocked. And the read, when you don't have anything arrived, if you read in Fstack, it will crash. So all the things need to be changed. Another way to change the event model is that we can use the Fstack-based event model to check what actually is there is any event happened. I give out the conversions between the Fstack event model and the traditional kernel event model used in the iProof. And the traditional iProof uses FD select model, which something like FD set. FD set is to set a socket to the read set. So for Fstack, there are 2 kind of changes can support this operation. Firstly, we can use the EV set model, which is supported by Fstack. We can EV set. You can add the socket to the kernel event set and check whether there is anything happened on that socket. Another event model which Fstack supports is the Fstack ePRO model, which is the same as the ePRO model in the Linux kernel, in the Freebsd kernel event model. We can pour the event on this socket. And use this table, you can convert all the things. all the things used in the traditional iProof to the Fstack model. And for the Fstack iProof, traditional iProof applications, at the left part is about the iProof running model. And we get blocked. When we run the test, we get blocked to get something like cookie, like some parameters to set, such as f size, any parameters. But it relies on the socket block, the file block the reading. But for Fstack, we can't block anything because we are in the same process of the whole things, and all the packet receiving is in the same process. If we blocked we can't receive any packet. So we have to modify the code to avoid any blocking operations, such as we have get cookie non-blocking and get parameter non-blocking and all things. And all the operations have to be re-enterable because this is in the whole single loop, in a single process. So we can't block anything, and it should make all these functions to be re-enterable. So we are doing these things to make iProof run. Besides the iProof porting to Fstack, in the future, we would like to enable the Fstack to be an independent library, which is a little similar than the VPP Hoststack, which can be simply use a LD preload to just link to the Fstack library to enable all the legacy network applications without no significant modifications. And therefore, if we want to use the Fstack as an independent library, we have to get the two things in two processes. One thing is for the DPDK processes to get all the packet and get all the packet receiving, packet sending, all things like that. And when we receive a packet, we put it to a shared virtual memory. In another process is about the applications. The applications with the LD preload to get linked to the Fstack and get all the packets from the shared virtual memory. All the shared virtual memory, we hold the memory. We have the memory manager APIs as VM APIs to get all the packets in the shared memory region. So with these methods, we can get Fstack as an independent user space network library as the VPP Hoststack. This is something about mTCP. mTCP is also a very popular user space TCP stack for today. mTCP is also a multi-thread model. Which when we get one socket, we can get one socket. We can use another thread to epoll another socket. And at the lower end, it uses user level packet IO library, which means PSIO, to get all the things wrong. And the PSIO library can also support DPDK. So it's a little different model from the Fstack, but it also has many high performance features, and it can address the inefficiencies from the ground up for packet IO and TCP collection management to the application interface. But one of the great limit is that mTCP is a independent implementation of the user space TCP stack. It's not a complete stack. So many kernel stack features it cannot support. So it is written independently, but Fstack uses a whole FreeBSD user space, FreeBSD network stack. So many features are kept. So, but for mTCP, many features lost because it's not a very complete network stack. And these days, we know that VPP is for vector packet processing and a very high performance, very high performance packet switching and routing, and it's a totally a user space network stack. The features, VPP Hoststack features that it has neuronal and a cubic congestion algorithm supported. It can support checksum offloading, can support SACK, faster retransmit, and TX pacing and the session layer had high-speed content networking support, and a Linux-compatible IWL TCP protocol tester, and it uses LD preload for legacy applications. So it can be used very portable. It is very portable to other legacy applications, and it can use the LD preload to support the traditional applications such as iPerf. We use the iPerf on this VPP Hoststack and do a test to compile that with the kernel. For the kernel side, kernel TCP/IP stack, we see that VPP Hoststack has a little higher performance than the kernel stack. We use the packet size to 64 bytes, and the NIC is 10 gigabit. But if we use more CPU cores, the difference can be bigger. So the VPP Hoststack has even more higher performance. For this table, it gives out a initial comparison between the current user space network stack, such as mTCP, fstack, and the VPP Hoststack. And all these three stacks can be supported on ARM. And they also support the BSD-like socket-like API and the feature abundant. And but for mTCP is a independent implementation, so its feature is not so rich as VPP Hoststack and fstack. And so we are putting more resources on the VPP Hoststack and fstack these days. And I think all three stacks has very good performance. And but they each have different restrictions, such as for VPP Hoststack, it can only be used with the VPP. And if we don't have the VPP, we don't have the VPP Hoststack. But for fstack, it now have to do the modifications to the legacy network applications with their socket, with the fstack API and the fstack socket API, or something like that. But for mTCP, it should also need to modify the legacy applications. So these days I think that the VPP Hoststack and fstack are more suitable if we can do some improvement to the two of them. For the next steps, we will continue NGX fstack performance testing with different file sizes. We will do a iPerf3 full enablement with fstack for performance testing. And for iPerf3, I think we would just enable the server side. For the client side, we should be compatible with the traditional iPerf3 client. I see some work for the iPerf on DPDK. Actually, it depends on another user space TCP/IP stack, which means ANS, accelerated network stack, ANS. And the iPerf3 on ANS, the limitation of iPerf3 on ANS is that I see it can't be compatible with the legacy iPerf3 client. So it also has some limitations. We also do the iPerf3 porting to fstack with a little different way. For VPP Hoststack, we would like to give more performance analysis with bottleneck analysis and resolution, and with improvement with memory ordering ordering changes. I work on the host stack primitive data structures and shared virtual memory files improvement and a message queue improvement. Understand the TCP state machine for one of the congestion control reasons and the new reload features. Yes, this is all my presentation today. Thank you.